Good morning, Math 111. This is section 9.1. So this is the last full chapter that we'll learn this semester. Hypothesis testing. So a hypothesis is something we take a good guess. What's fascinating is on the news right now, there's all kinds of hypothesis and testing and what's going on. So you guys have good statistical knowledge to help you out there. All right, so 9.1, we're going to get into what are statistical tests. So the basis of this, the thing you really have to get a grasp on is the fact that sometimes if it looks like the mean has changed or that something has changed, perhaps it hasn't really changed. So perhaps it's not significant enough. It's not a big enough sample. It's not a big enough change. Perhaps it was just a sample that told you something, but maybe not everything was totally clear, or it showed you something that wasn't really going on. So that's the basis of what we're talking about. I'm going to try to get, so when we state a hypothesis, we have a new symbol, H, okay? H for hypothesis, so not a super hard thing to remember. You see that little zero right there. We say H naught is how we say that. We say H naught. And H naught literally means nothing has changed. So zero, nothing has changed. So H naught, nothing has changed. We'll also have H1, and I'm going to go ahead and put the colon in there, so I hope you can see that little colon. So H1, this is H1, or alternative hypothesis, A-L-T-E-R. Alternative hypothesis. This is what do I think has changed? So null hypothesis, alternative hypothesis. So just get comfortable with those terms. So for instance, I might say that H naught mu is equal to, so this is how I write it out. So this one is 6.5 feet. It's the average height of an NBA basketball player. I might say, I think it's gotten bigger. They seem taller. When we moved to Indiana, I thought for sure that they grew them taller here. So H naught mu is equal to 6.5 feet. H1 mu is greater than 6.5 feet. I'm going to keep going. So we have this null hypothesis, our alternative hypothesis, and the point is, and this symbol is important, is this greater than or less than or just not equal to? So let me write those down. Let's see. We can have greater than, we can have less than, or simply just not equal to. So this information tells us what is really going on. So the null hypothesis is a statement that's under investigation. The alternative hypothesis is the thing that I think has changed. All right, I am going to close the curtain. I think it's too bright in here. So as we get into these alternative hypotheses, we're going to use that same foundational information that helps us decide whether we're going to have, we're going to use the Z-chart or the T-chart. It'll look a lot like Chapter 8. So Section 9.1, we're primarily using Z. Section 9.2, we're primarily using T. And then in Section 9.3, we'll be testing probabilities, little p. So again, we come back to using Z. So it follows that same cadence that we had previously. All right, so let's say a manufacturer advises that his new subcompact model gets 47 miles per gallon. Let mu be the mean of the mileage distribution for these cars. So mu is mileage. So H naught, mu is equal to 47 miles per gallon. H1, I think they overstated it. I think that really they're not getting 47 miles per gallon. Now there's some truth in advertising things they have to. They can get in big trouble. Volkswagen actually got in big trouble a few years ago because they overstated the mileage for their vehicles. So that actually can get you in huge trouble, legal trouble. I think they actually had to replace vehicles for people or buy them back. So if I want to say, by the way, really important thing, H naught colon mu, let me make that colon a little darker so that you can see it. Okay. And I am on slide 13, by the way, if you're following along. H naught mu is equal to 47 miles per gallon. I think that really it's less than that. So H1 colon mu is less than 47 miles per gallon. So that's how I would state that. That's my H naught and then my H1. So a couple things just to kind of simplify it. H naught is always going to have an equal sign. H1 will have a less than, a greater than, or an equal sign. Pay attention to this colon. So H naught colon mu is equal to. One of the errors students make is say H naught is equal to 47 miles per gallon. It's not. H naught is like saying on the blue page, it says mu is equal to 47 miles per gallon. On the green page, mu is less than 47 miles per gallon. So it's simply H naught and H1, this null hypothesis and alternative hypothesis, are simply stating, you're simply saying this is this thing, okay? So what is this thing? This thing is that mu is equal to 47. This thing is mu is less than 47. So keep track of that. So type of hypothesis, we have left-tailed, right-tailed, and two-tailed. So let's write those down. Actually, there's a really nice chart right here. Actually, I even oh no, that's not that one there. So let me pull this up a little closer. So if you'll see, the first one says, what is my null hypothesis? The second, shall we call it column, they don't actually have boxes on them, but second boxes is my left-tailed test. So H1 mu is less than K. K is just some value. In this last case, it was the 47 miles per gallon. The third box says H1 is mu is greater than K. That's right-tailed. That is like the NBA players that we thought had gotten taller. And then the last box says H1 mu is just not equal to mu. That means it could be bigger, it could be smaller. I know something has changed. I just don't know what that thing is. I just don't know if it's gotten bigger or smaller. So you have three different ways to do that. Again, we're going to start with this. The X is a normal distribution. Connected those. And sigma is known. And of course, how do we know sigma if we don't know X, mu? If we don't know mu, I don't know. But there could be on some planet, you had some knowledge that that's how that works. So once you have your null and alternative hypothesis, so you always start by stating my null hypothesis, which is mu is equal to something. H1 is mu is less than, greater than, or simply not equal to something. And then we have to calculate our t values or z values in this case and work through that. So remember mu and p and sigma, those are population values. Don't lose track of those. Got to keep up with those. So let's see, I'm trying to get through this really quickly. We are on slide 23. We're going to go back and use X bar and Z. So Z equals X bar minus mu over sigma divided by the square root of n. So remember that formula from, what was that, about 7.4, 7.5? That same formula. So on your formula sheet, it will show it back under chapter 7 because that's where that is on the list. So Z equals X bar minus mu sigma over the square root of n. And remember, n is our sample size. Da, da, da. So here's one of my favorite examples in the whole book. Rosie is an aging sheepdog in Montana who gets regular checkups from her owner, the local veterinarian. Let X be a random variable that expresses Rosie's resting heart rate. So if you want to see, some of you have done some of that. If you're in kinesiology, you've done resting heart rate versus active heart rate and kind of looked at comparisons, and perhaps even you've kept track to see how your general physical condition is. But the vet, who happens to be her owner, said that she has taken some samples of Rosie's heartbeat, and she has a sigma of 12 because she just knows that. And she goes to a manual that tells them, you know, for an Old English sheepdog, what should be the resting heart rate. And it's 115 beats per minute. But Rosie's owner thinks that it's really less than that. Thinks that sweet old Rosie is slowing down. So the funny thing is, all three of my dogs are out here. They usually are while I'm doing these lectures, recording my lectures. And we have a sweet old dog that's about 12 that is one of those that's out here. So that's the manual. And then she has taken these readings. There's a 93, 109, 110, 89, 112, and 117. So over, 6 weeks? So n equals 6. So over 6 weeks, she's taking these readings and finds that X bar is equal to 105. So if I were to look at this, I'd say 105 versus 115. Well, by golly, it certainly has. Oops, dropped my eraser there. It certainly has slowed down. But then I go, wait a second. That's only 6 samples. Did it really slow down? Or was it just that I caught Rosie when she was in a particularly relaxed state? I mean, what's going on? So we have our null and alternative hypothesis. So null hypothesis colon mu equals 115 beats per minute. H1, my alternative hypothesis, colon mu is less than, shouldn't be equal to, less than 115 beats per minute. I'm on slide 27, if you're following along. So we need to do a sample. And I'm going to skip ahead because what they do is kind of give some general information. I'm going to draw a normal distribution. So we know that mu is 115. Okay, that was my mu, 115. And really, Rosie is down here at 105. So it kind of looks like that things are slowing down. So what we want to know, what we're testing, okay, because we talked about this as hypothesis testing, what is the chance that this sample tells me what's really going on versus what is the chance that it's a fluky sample? So fluky, like I took the sample and it just didn't really tell me what was going on. We all know that can happen. Maybe Rosie was, maybe she was sick temporarily, or maybe The vet caught her when it was late at night and the dog was just done and she was really, really relaxed, okay? Not sure. That's what we're testing. Does this sample accurately tell me what's going on, or is there really something else going on? So we check the sample. This is a great little graphic that helps us understand what we're looking for is that tail is as small as possible. So the smaller the value on that tail, whether it's left-tailed, right-tailed, or two-tailed, okay, so if it's not equal to, it's two-tailed. So whatever that tail is telling us, that's what we're comparing, or we will be comparing. We'll get there. So it has a normal distribution because they told us that, and we have N and sigma. So I'm going to do my test statistic. Let me get rid of some space here. So Z equals X bar minus mu sigma over the square root of N. So I have 105 minus 115 over 12 divided by the square root of 6. So that gives me a Z value of negative 2.04. You'll expect that these p-values that we're going to calculate will be small. Now remember, this is going to be big P because it's for this situation. So the probability, so don't forget all this stuff from chapter 7, probability that X is less than 105 is equal to the probability that Z is less than negative 2.04. And again, I'm going to go look it up on my Z chart, find that probability is 0.207. Now, what's interesting is, I don't know, is that big or small? Okay, I have to give you some sort of guideline that says whether that's big or small. So I'm going to keep going because I need to introduce a new concept. So this is the p-value, okay? The p-value of the test. And again, the smaller that is, the better chance that this is an accurate sample. So 2.07% is pretty small, okay? That's pretty small. I'm going to hang on to that 2.07 for a second, because that's Rosie's number. And so the lower the p-value, I'm on slide 35 at this point, the lower the p-value, the greater likelihood of obtaining the same or very similar results. So here's another version of the chart that talks about left-tailed, right-tailed. So left-tail, mu is less than, and that's what Rosie's owner thinks, is that it's less than. And see how that little tail down there, that little pink area, that's what we're looking for. The smaller that is, the more likely that this is a good sample, a valid change, that yes, something is going on. And then we have the right-tailed. So the smaller that is, the more likely that there's something going on. And then the bottom one is a two-tailed. So we have, it could have been less than, or it could have been greater than. We just know something has changed. And those are tricky. I might do a whole short video on those because those can be tricky. All right, I'm going to stop here and then do another separate video on types of errors.